episode, we ended by speaking about this idea of how do we define matter? How is it that we can start to break matter down into different camps so that we can then talk about it a little bit clearer? And we ended with this idea of we have pure substances and we have mixtures. Now, the next question that comes up usually is, well, how do I describe that pure substance? How can I describe that mixture? And usually we're going to refer to these two broad terms that we have listed here, which is a physical versus a chemical property. Okay, now they sound very similar, but they each talk about distinctively unique things. So let's start off with the easier of the two, in my mind, at least the easier of the two to define and understand. And that is, what is a physical property? So a physical property is one that we can observe, and this is critical, without altering the substance. So things like, for example, the color of an object, right? The mass of an object, the height, the density, right? All of these are things that we can observe. We can actually physically take these measurements and the object stays the same, right? We didn't alter what it was. It didn't become a new substance, et cetera, et cetera. Now, this is critical because this is the distinction between my physical and chemical. You see, in order to observe a chemical property, unfortunately, what we are going to do is that we are literally going to destroy the original substance in order to observe its chemical characteristic or its chemical property. Common ones would be things like, how corrosive is a substance, how combustible or its combustibility, right? Also known as flammable. Does it oxidize? Now, that's a fancy term. We'll keep it a little bit more simple right now. We'll say, does the object, like iron, rust, right? So when we say iron oxidizes, we say that iron rusted, right? So all of these terms are things that we can observe them, we can measure them. But in doing so, the object is now forever altered, right? And usually it can't be recovered. So is, for example, paper flammable? The answer is yes. And I could even probably figure out things like the flash point or how flammable or how combustible the paper is. But unfortunately, once I burn it, I no longer have paper. So I've learned a lot about it, but I've now lost that substance forever. So now that we understand what a physical and chemical property is, the next question that comes up is, well, what happens when we alter a pure substance or mixture? What happens when we do something to change the way that maybe they appear, maybe the way they operate or the way they behave or the physical or chemical properties about them? What happens when a change happens to that substance? And so again, just like we had physical and chemical properties, we have physical and chemical changes. Now, in a nutshell, here's what it comes down to. A physical change is reversible. Okay, a physical change is reversible. We can undo a physical change. So examples of physical change: you can tear or cut a piece of paper. You can color said piece of paper. You can add more pieces of paper. You can take away pieces of paper, right? All of those are things that can be reversed, right? As long as it can be reversed, then it's a physical change. Now, there's one set of physical changes that are not so obvious, right? Because they are reversible, but it's not something that we often think about in terms of a physical change. And those are changes of state, not like moving from Colorado to New York. It's not that change of state. Change of state meaning something is melting, boiling, freezing, condensing, subliming, right? Any change of state in which you go from a solid to a liquid to a gas, or solid to a gas directly, any change of state is considered to be a physical change. Why? Because in every change of state, we can undo it. If I take an ice cube and I put it on my kitchen counter and I wait a little while, after a while I'm going to have a puddle of water. But if I take that same puddle of water and I put it back into my little ice mold and put it in the freezer, guess what I'm going to come back to? The same exact ice cube. And nothing will have, quote unquote, changed. Now again, physical changes, the big takeaway is that they are reversible. You can bring back your original substance, okay? As opposed to something like a chemical change. In a chemical change, we have permanently altered the substance. Again, there's no coming back. So, as we spoke about before, remember we talked about chemical properties. In a chemical property, we said that in order to observe it, you could no longer interact with that original substance. Well, in a chemical change, we've forever altered our substance. So, for example, I burned the substance, right? Or it combusted. It underwent oxidation. Remember, that was my fancy term for rusting, right? It decomposed, right? Or it deteriorated in some way. We could even talk about chemical changes in terms of if we had something like a nuclear substance, right? Something that's breaking down into different substances. Again, the original one is no longer there. So all of these are examples of chemical changes. And why is it important to understand the distinction between a physical and chemical change? Because everything we do in chemistry is going to, in some way, shape, or form, always come back to this idea. When we study matter and when we look at how matter behaves, we're going to be observing what happens when we do something to alter it, what happens on the other side of that chemical process. And one of the most common ways that we will use this idea of a physical and a chemical change is to separate a mixture. Now, as we discussed earlier, a mixture was two or more pure substances that were just juxtaposed. They were physically next to one another. But notice I keep using that word physically, right? Now we have a new definition of a physical change. And so since mixtures are nothing more than a bunch of pure substances hanging out next to one another, what I can then use in separating mixture are physical means. Another way to think about it is I can literally use physical force to separate out a mixture. So what do we mean by this? Well, let's take a look at the example that I have here. Let us suppose that this was literally a pile of salt and pepper that I had mixed together. Now, what I would be able to observe is, sake of argument, we'll call these yellow ones, this could be my salt, right? We'll call these green ones down here, this would be my pepper, right? And so I have a mixture right now of these two distinctive substances that are just placed next to one another. And so the question becomes, well, I don't want to have salt and pepper together. I want to separate them out. What could I do? Now, don't get me wrong. This is going to take me a hot minute, but I could, in theory, sit there and start picking these up literally one at a time. So I could grab this guy here, boop, and move him over here, right? And then I could grab this guy over here, right? And he looks the same, so I can start to put him over here, right? And this guy over here, and so on and so forth, right? And so I start to create a little stack of salt. Now, the same trick can be done, and I can grab these guys here. Now this becomes my little stack of pepper, right? And notice that the whole time that I'm doing this, what I'm able to do is by using physical force, you literally see me right now picking up each individual particle, I am now separating my mixture into, over here, we have my new stack of pepper, sake of argument, right? And over here, this is my new stack of salt, right? And so by physically picking up one at a time, I have now separated out the mixture into its two unique pure substances. Well, what happens if I have a mixture that it's not so obvious the way I could separate it? For example, what were to happen if I had, let's say, salt water? Now again, salt water, I have salt, sodium chloride, mixed in with a bunch of H2O, water. But it's a homogeneous mixture, and this is something that's so finely broken up that I can't see where the salt is. I can't literally sit there and take my magical tweezers and pick up each individual salt particle and separate it from the water. So what do we do when we don't have as an obvious a way to separate my mixture? Well, in these cases, right, when physical force is not as clear a method, we have a couple of options that we can use in order to separate these two substances. The first one we refer to as distillation. Okay, and distillation is a process whereby we take the difference in boiling points of substances and we use that to have one substance leave the other. So let's use this example of sake of argument, salt water, right? So let's pretend that down here in this container over here, right? So yoink, right there, right? This is my mixture of A and B. This is my mixture of salt water. All right, so this is salt water. Now, well, salt water is made up of two substances, like we said, sodium chloride and H2O. Now, off the top of my head, I don't know what the boiling point of sodium chloride is. I know it's really freaking high. So think 1,000 or thousands of degrees Celsius. But I do know that water will boil at 100 degrees Celsius. So if I sit here and I take my mixture of salt water, A and B, and I start to heat it up. So here's my little fire down here at the bottom, right? And so I now start to heat up the mixture. Well, the temperature of the mixture is going to start to rise and rise and rise. It'll hit 70, 80, 90, 100 degrees Celsius. And at a certain point, what I'm going to start to notice is I'm going to see steam coming up, or let me say that a different way. As the steam starts to bubble up, let's say that this is going to be particle A. So this is particle A, which we'll call the water. And so what happens? The water or the water vapor, the steam, is going to rise on up. It's going to get trapped up into this little area here, which we call the condenser. And eventually it's going to go from gas, it's actually going to start to become a liquid. And it's going to start literally drip, drip, drip coming down on the other side. So eventually what will occur is over here, I will have pure H2O, or particle A. And on the other side, I'm going to be left with just particle B. And my mixture will now be isolated, and I'm no longer going to see the salt with the water. I will now have isolated and have water on one side, salt on the other. All right, so this is how distillation works. Another common use of distillation, this is usually how we make spirits, right? Or how we make, alcohol. When a distillery, let's say a brewery, creates their first batch, it's called a mash because in it you have alcohol, what they're looking for, and you have a bunch of water. So to separate out the two, you heat up that mash, you heat up that mixture, the alcohol boils out first, the water gets left behind. So this is, again, by using boiling point, remember boiling, physical change, reversible, by using distillation, we can use these differences in their boiling points to isolate and separate substance 1 from substance 2. Okay. Now, the other method that can also be used is filtration. And in filtration, what's going to happen is, again, we'll use the same salt water example. But if this represents, sake of argument, let's make these, and I'm going to lie a little bit here, but let's just pretend that this is a molecule. This one here is NaCl. The big ones are NaCl. The little ones are going to be my water. Right? So let us pretend that these big guys here represent the large sodium chloride particles. Well, in filtration, what I do, you might have heard of this sometimes as osmosis, right? But what I'm going to do is I'm basically going to take this whole mixture and I'm going to push it towards some type of screen, right? Some type of filter. Maybe it's a paper or something along those lines. Now, what you can imagine is as these particles move over and they come into contact with the screen, it looks like to me that these big guys here, these big sodium chloride particles, are not going to be able to fit through the mesh, right? And the best way you can describe it is exactly that. As these particles pass through, as they start to move towards the mesh, what's going to happen is that these these sodium chloride particles are going to get stuck on one side of the mesh. But what we're going to notice is that these water particles here, since they're smaller, they're actually going to be able to pass through to the other side of the mesh. And so by using this idea of filtration, what happened was we used the size of the particles to separate one from the other. And so both of these methods can be used to take my mixture and isolate them into their original pure substances. Again, In both of these instances, whether we're using filtration, distillation, whether we're physically moving particles apart and separating them, whatever we're doing, can we go backwards and mix everything back up? The answer is yes, because I used a physical change or a physical means to actually isolate and separate. And as long as it's reversible, right, and we can go back, then it's a physical process. The minute I burn or I oxidize or I do something where the substance I cook or where the substance is permanently altered, then in that case it's going to be a chemical change. So we take it one step at a time, one tick at a talk, and you'll be there in virtually no time.